Anyone who's worked with me knows that IT and software things just break as soon as I've touched it. The remote pointers decided not to work. I did present ages ago, and as soon as I went to the first slide, PowerPoint crashed. Right, bit of my history. I've been in the industry 20 odd years. I started at a company called Wolfson, where we had our own in-house tools. I was technical project lead for about 18 plus devices, as well as architecting some of the EDA tools. Sort of got burnt out on that after 12 years, and then moved to a small company for a couple of years before joining Dialog, which is now Renesas. I got roped into working on Accelera standards, so I'm chair of System Verilog AMS. I then helped Steve Tim out on UVM mixed signal. In fact, if you look at the draft document, most of the diagrams, text is work I did. Someone else fixed all my spelling mistakes, by the way. And then I'm more recently dragged into System Verilog MSI, which is basically looking at replacements for Connect modules. So today's presentation is basically for digital mixed signal modeling. We're going to use signal flow equations instead of these two-terminal devices that you can get hold of. A bit later, you're going to have a presentation with someone else saying, don't use signal modeling, use two-terminal devices, which just shows this whole industry there really needs to be a standard, because I've seen 3 or 4 different ways of doing this stuff, which means if you create a model, you can't share it easily, or there's no way of getting an industry model out. So, right, so the agenda, we'll go through the modeling styles. I'm going to go through the S domain to the Z domain. So for those who can't remember, that's Laplace equations to the Z domain, your digital filters. I'll go through a CAP example, some known issues, and then at the end of all of this, where I did loads of work, writing pages and pages of maths out that I've got in my book, showed it to a work colleague who went, oh, you know you can do that in Python in one line. I hate Python now. I'm not writing a test bench in it, that's for sure. Right. Again, DMS is missold as the replacement for AMS. So this is a statement a work colleague came up, which was digital mixed signal methodology directs not to structurally connect two terminal devices together in an arbitrary network, but instead to model those networks with a signal transfer modeling. So this presentation aims to explain why and how. So my attitude has always been not take, a passive network of resistors and model it the same way, is collapse that down into a single equation. You would do that in Verilog A or Verilog AMS so that you get the speed up. So just a few things. Analog lib modeling, you could do a schematic representation. It's very easy to do. You can get an analog guide to draw it. It's more visual, but you tend to only get about 10 times back to speed up. In fact, you can absolutely crowbar your DMS simulations if you get it wrong. Signal transfer, you can get a lot faster speed up. So there is a company called Scientific Analog that had tried, makes a product that basically sells like transistors and all the rest that you can use in DMS modeling. They tried to push it into the UVM mixed signal. It got no traction. We've tried it internally. I know other people have tried it, and it's not as good as it's put on the marketing paper. Other companies do make a library of passive components, which does make you think you can draw an arbitrary schematic. But, as Andrew Beckett's just said, yeah, you don't need to replicate the schematic. And often at the moment, some of these are encrypted because they've got vendor-specific extensions. And so it's hard to debug. So, yeah, the Laplace transform. So the Laplace transform is your S domain. So if you ever take a CAP, you can write it as an S domain, SC, etc. and it's more suited to the frequency domain for modeling stuff. So you've got here like a resistor just maps to a normal resistor. A capacitor can either be modeled as a voltage source with a resistor or a current source with a parallel impedance. And you can do inductors. Notice there's no diode here, and that's because the diode isn't a linear differential equation. And diodes are an absolute nightmare in DMS, as I'm dealing with one at the moment. Trying to get them to work in all cases is really hard. You'll get it working, someone will change one thing, and the whole DMS modeling system of your whole SoC stops working. So you can get speed up, but you can also then bottleneck a project for some time. So the Z domain can be considered as the discrete equivalent for the Laplace. Most people at university will remember that triangle, S, T, and Z, the different domains that you can operate in. Might have been some time ago. So I had to relearn it as well. So what you can do is you can take a S-domain equation. So it's quite easy to take analog components, create an S-domain equation of all the passive elements together. Then you can use the bilinear transform and replace S with that value there, and that will convert it to like a Z-domain transfer. So this is no different for those who had created old analog filters and wanted a digital filter. It's just, if you're not doing it day to day, it seems a bit complex. But I say when you've got energy elements, you need to do these steps to get it to work in a event-based solver. So if we take a capacitor, your time domain is I equals C dV by dt. Put that in the Laplace domain, it's I equals SCV. Hopefully that's all okay for everyone. We can take the bilinear transform. Where I had Z, all I've just done is multiply through by Z to the -1, because I can't go forward in time. Z to the -1 is your previous sample, so it's just a delay. That's the trapezoidal rule. So yeah, that does mean you could get trapezoidal ringing in your digital models. I'm not sure if that's the problem I've got or something else. It's so hard to debug some of this stuff. So what you can do is shove it all together. This maths is correct, I have checked it. So you do the I equals 2 times the frequency times the C, V of t, and then multiply it by the differences. And what you end up with is an equation at the bottom which takes the current into the cap currently, the current from the previous time step divided by basically the impedance of the cap plus the old voltage, and that will give you the next voltage on the cap. So as you imagine, you're basically working out how much current has gone in between the last time point and this time point over the impedance of the cap. And so therefore you've now got a very simple signal transfer equation. Other methods you can use: forward Euler's, backward Euler's method. So anyone who's done an analog sim will recognize some of these names. So you don't have to use the bilinear transform. It's the one I used, which probably made all my maths far more complex than it needed to be to start off with. Then you can just map that to some Verilog code. So you've got a hash TS *1 second. So this always block will wait at that point until that timeout happens, and then execute these 4 lines of code here, and then go back to the beginning and wait. So I_1 gets the previous time sample. I gets the current probe going into the cap, and I'll show you how I do that. V_1 gets the last voltage, and then basically I've applied the equation from the previous slide. Now, I_1 looks a bit odd. Most people would go, oh, use a packed array or some other method of doing that. Packed arrays are expensive. They're slower. This is a model. What you want is, when you write a model, is you do a profile of the chip, and your model is not the thing taking the CPU time. It's someone else's code, normally the test bench. You want your models to be really, really fast. So just simple things like this can make a difference. I often want to see all the UVM stuff high up the list and blame someone else. There are things you could do. You could try dynamically changing the time scale, like analog solvers. But again, you're not trying to replicate an analog solver. What you're trying to replicate is what does a cap look like? And you're trying to model the effects in a digital sim to catch verification errors, such as, you know, does the comparator trip? You're not trying to model noise and all the rest. That's for AMS. Yeah, so I modeled the cap as a single voltage source with a resistance. So the resistor was set as the ESR. I probed the voltage as the node.V. So the V is the element in the UDN. And then sample it. Now, of course, ideally, we all want two terminal devices because often our caps aren't bolted to ground. There are various ways of doing it. The way everyone tries to do it is basically impedance balancing, which is making a cap look like a voltage source with a series resistance and mirror it using Thevenin and Norton equivalents. And that's how you get it to work. But it's event-driven. So the problem is you can get one event triggering another on these two terminal devices. It just constantly loops around and never stops because it's not an analog solver. So it can be done, but you got to be careful. So I saw you an ideal cap. No one has an ideal cap. You've always got some sort of series R in there. So I added a parallel R and a series R, and that's what the equation came to. I didn't get it right first time. I didn't get it right second or third time, actually. And then I decided I'd put an inductor in there because someone thought that was a good idea. Jesus, yeah, don't do that. I don't know whether I ever got it right until I used Python. So there are things you can do to optimize this. You've got an equation like this, and it could be that it's only the output only changes by 1e to the minus 32. I don't need to change my electrical net when the output is only changed by 1e to the minus 32. Choose a sensible delta. You know, that if the output voltage isn't going to change from the previous one by more than a microvolt, then don't do anything. To get this to work, I basically had to borrow a feature from Verilog AMS called driver receiver segregation, which is basically in most of the tools now anyway, and it's going to be in System Verilog standard soon. And just doing that has made a real difference in the simulation performance. So just basically getting rid of small noises that you don't care about. So you can think of it as the Abstol in an analog solver. The other thing is there's no point in calculating all those coefficients each time. You know, you're not going to be dynamically changing the resistance all the time. So those can be just calculated once. And that, again, these always loops are toggling quite often. So if you can make a single optimization like that, it makes a big difference. Some of these things will have, you know, up to 500,000 events in a simulation, if not more. So cutting out a line of code makes a big difference. So I thought I'd got the inductor part working, and then it all went wrong. And I don't know whether it was my equation or anything else. The problem is I came at it with a digital mind, handed it to an analog guy, and he went, yeah, but remember, by adding an inductor in, you've given the circuit gain. The inductor causes gain to come up there. So instead of having a normal cap roll-off, which would be down there, and I've got no filtering in the circuit, I basically made high frequency stuff generate noise and get gain. So I think that's what caused my circuit to become unstable in DMS. But again, it's quite hard to tell. So I haven't got to the bottom of that. Possible solutions: you could change the sampling period. You could add a pre and post filter. question is do I really need to model the inductor in the cap? Is it going to gain me anything in my digital modeling or verification? Probably not. You know, in all honesty, if I'm looking at the ESL in a cap, I probably should be running an AMS simulation. It's going to get it a lot better than I can. So some corner cases with the cap model I've got like that, and it being connected to another a UDN. The UDN is just driven by a discrete value. So you could go from 0 volts, 0 ohms to 100 volts with 1 ohm in one step. When the cap samples it, it's going to get a massive current flow that could make the cap value go to a stupid value, because it's going to think it's had that current flowing in it for that sample period. So you then end up with a cap voltage going too high, then too low, and if you're unlucky, which I always seem to be, it then oscillates and then goes to not a number. So you need to put some clamping in. So I won't go there. So what I did was I basically rearranged the equation that if the current going in was going to be such that it was going to generate a new cap voltage that was above or below the current supplies it was attached to, rearrange this equation to make sure I of t and I of t minus 1 match that result, and v of t and v of t minus 1 were the same. That meant that the next time the loop got executed, it was in equilibrium. And so you have to rearrange the equation as such. When to use it is your choice, but you have to have access to the external drivers. So this is all this DRS technology. SIE is another name. Get external drivers, I think, is another name. So there's some optimizations I've done. I disable sampling when it's not needed, refactoring the code and profiling. Remember, you don't want to write a model that slows the sim down. You want someone in the test bench who's written UVM to slow it down. Then you could have told them that using Python would have been better. Yeah, change the sampling frequency. Don't probe everything. UDNs are expensive to probe. You know, they're structures. So we saw on the previous slide, some of them had 5 fields. If you've got hundreds of those nets, that's a lot of data to keep dumping. Yeah, try and merge all the passives into a single transfer function. Yeah, some useful things that have come out. System Verilog 2023 added support in for a UDN in the tran-if statement. So if you really want an ideal switch, you can now do it. So you could actually have a flexible test bench that at time 0 you could rewire. If one port is meant to be a reference, disable the bidirectionality because it's problematic. As I said, avoid complex networks and multiple updates. So I did all of that, did all that maths, got it all working, and then I was chatting to a work colleague who went, "Oh, give me the equation. I think you can do it in Python." And so he gave me some code, and you need to import SymPy, whatever that does. For the top line here, it sets up some variables. I have no idea what positive equals true does. He just told me to write it. Init printing, I copied and pasted what he had. Then I've basically written the equation in here, V, and that's equals that. Then this has told him to solve the equation for V divided by I, which will give me H of S. I've then got S of Z, which is basically my bilinear transform. I tell it to substitute it. I can then get it to print it all out. So gone are the pages and pages of maths. 22, 20, 2 more minutes. Yeah. But what you can do, as I've run out of time, is you can you could just do something like this. Get the equation, get it to write out denominators, and then you've actually got the equation that you need to use. So my thinking going forward was actually that you could just dynamically create this by calling Python from system Verilog. Though I wasn't going to do that. Right, I've run out of time. Any questions? Right.
This is really nice, Daniel. Here, I wanted to just comment that the issue you can get with the cat model in particular, if you try to use it as a high pass, you can wind up with aliasing because your signals are higher than your sample rate. You violate your Nyquist criterion, and you end up with aliasing.
Yeah,
and that's just something you have to watch out for when using that kind of model.
Thanks, Daniel. Yeah, there are many caveats. Right, the